In this video, I'm going to talk about Lenz's law. Lenz's law is going to give us the direction of the induced current when the magnetic flux through a loop changes. Let's take a look back at one of the experiments we saw previously. If you move a magnet towards a loop, there will be a current induced. You can see that this loop here of wire is just connected to an ammeter. There's no battery or anything, but as you move the magnet towards it, you can see a current -1 milliamps. If you hold the magnet stationary, there is no current. You see it goes back to 0. And then if you take the magnet away from the loop, now there's a current induced in the opposite direction, which is represented here with a positive current instead of a negative, so in the opposite direction as before. So Lenz's law is a mouthful. Here is what it says. The induced EMF produces a current that creates a magnetic field with flux opposing the change in the original flux. What in the world does that mean? So basically, we know that there's a current induced in a loop of wire if the flux through that loop is changing. We saw that in the previous 3 videos. So you know that whenever you have a current, that is going to produce its own magnetic field. So if there's an induced current in a loop, now you also have an induced magnetic field in that loop. That induced magnetic field is what is going to oppose the original change in magnetic flux that caused that induced current in the first place. So how does it oppose the original changing flux? So I've written some steps to kind of help us understand how to use Lenz's law. We're going to use these steps as we go over the following example. First thing is you need to figure out which way is the original field going. And then figure out, is the flux through that loop increasing or decreasing? If the flux through the loop is increasing, then the induced magnetic field is going to be opposite the applied field. You see how it's opposing the original change in flux? The flux was increasing, so now the induced field wants to produce a magnetic field in the opposite direction to oppose the fact that the flux is increasing. Now, if the flux through the loop was decreasing, then the induced field will be in the same direction as the applied magnetic field. Again, it's opposing the change in the flux. If the flux is decreasing, the field wants to be in the same direction to kind of augment that original field that's decreasing, so now you're trying to make it increase again to oppose the fact that it was decreasing. So you just ask yourself these 2 questions. And the third step, now that you know which way the induced magnetic field is going to be, use right-hand rule number 2 to figure out what's the direction of the induced current that will generate that induced field that you just found. I know that is a lot to take in. Let's go ahead and do an example. So we have a bar magnet is moved to the right toward a stationary loop of wire. The first step is to find out which way was that applied magnetic field. Well, you can see the magnetic field always points away from the North Pole, right, and towards that South Pole. So at the location of the loop, that magnetic field is pointing to the right. That's step number 1. Which way is that field? Step number 2, is the flux through that loop increasing or decreasing? Well, the magnet is getting closer to the loop. We know that the stronger you are to the magnet, the closer those lines are, the stronger the field. So if the magnet is getting closer to the loop, that means that the field through the loop is increasing. That means that you are increasing the flux through that loop. So the magnetic flux is increasing with time. So that means that A applies to us. The flux is increasing, so the induced field is going to be opposite of the applied field. So what I like to do is I like to always write down, okay, the original field was to the right, the flux was increasing, so the induced field is going to be in the opposite direction. The induced field points to the left. And the last step is now to figure out, okay, what current induced in that loop will give us an induced magnetic field to the left. So do you remember that right-hand rule number 2? You're going to have a current induced in this loop. So you fold your fingers in the direction of that loop. It's kind of hard for me to draw, but if I try to draw it, you got the knuckles here. And, I'm not an artist here, but you've got your fingers kind of going this way. You've got your thumb over here. And you've got your hand. So you can see I was trying to create like a fist. I don't know how many fingers we have there, but you can see that my fingers are curling this way, which is this way. And then right hand rule number 2 says, then that means that the thumb, you actually draw it perpendicular, or you point your thumb this way. There we go. Again, not the best picture, but hopefully you can kind of see what I'm trying to do here. There we go. So if your fingers are curling this way, which is given by this arrow here, the thumb points in the direction of the field, which is to the left. That means that the induced current must be this way. So how do we describe this way? Well, we can say that if our eye is over here, if we're looking at the loop from the left-hand side, then this current, which is flowing this way, is going counterclockwise. So CCW counterclockwise. So just to summarize, the original field was going to the left and the flux was increasing. The induced current produces a field to oppose that change. The induced current produces a field to the left, so that now the flux is not increasing as much as this magnet is getting closer. So we'll have a lot more examples of Lenz's law, but that is all for now.